say let's say your initial velocity, remember the initial velocity, the orbital velocity of the Earth is 29,860. Okay, so over here Vx is 0. That means I'm starting with the sun at the center, and then I have the Earth here 1 AU away, and then I have the velocity Vy is equal to then I could make the Vy whatever I want. So if I make the Vy 29,860, enter. So basically what I did is I made the initial velocity the same as what we know to be the orbital velocity. So 29,860. And then the distance is 1 AU, right? X final. So 1.49 something 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 times 10 to the 11 meters, right? And then y starts with 0. Okay? Then after you do that, the rest of it is just sort of corrects itself, and then you go like this, and then you highlight the whole thing, right? You highlight the whole thing. What was the way of doing it if I want to go all the way to the bottom? I think shift, right? Then I go over here, and then I say insert, insert, and then I go to X scatter plot. And I don't, no, actually I could do this one. Scatter with smooth lines and markers. Scatter with straight lines and markers. This one is the one I chose. Yeah. Then I could cut that and put it on the second sheet. Like make it like a square shape. So what will this have proven? This proves that an object at the 1 AU away with the correct speed is going to go, and you see over there is 1.5 times 10 to the 11th, negative 1.5 times 10 to the 11th, and keeps making a circle. You see? So we basically proved that with that necessary velocity, 29,860, and with the sun's mass, right, with that distance of 1 AU, that's the velocity that you need in order to go around the sun safely without winding into the sun or without escaping from the sun. So Excel, just by using the laws of the equations of kinematics, is giving you the same answer that you get by doing this equation. GMM over R squared is MB squared over R, MM cancel, and then R cancel. B is equal to square root of GM over R. The orbital velocity is square root of GM over R, right? But notice we didn't use this equation when we did this at all. That's the orbital velocity of the Earth. We didn't use it at all. We just simply put the location of the Earth, we broke up the gravity into X and Y components, and then we did simple kinematics, and you get the answer. So this is going to be the orbit of the Earth for 3 years, I think. And as many columns as you created, as many rows as you created. I think I created 27,669 rows, which is 27,669 hours, right? How many years is that? I have 27,000 669 hours. So that's going to be 24 hours in a day, right? 24 hours a day, and then 365 and a quarter days is a year. Okay, so about 3.16 years. So a little bit more than 3 years. And notice that the orbit stayed circular for 3 years, right? Perfect. Now we can play around with it, that the fun really begins. We can say, what if the Earth was at the same location, but had a smaller velocity? So let's say, for example, 25,000 meters per second. So what did I do? I gave it a lesser velocity than it needs to have. So always keep that in mind. This one is the actual true velocity. So now I gave it 25,000. So what should happen to the Earth? Or to any other planet? Should it wind itself closer to the sun, or should it go further and further away? Make a guess and then go to sheet 2 and see if your answer, if your guess is true. Well, this one is kind of going over itself. Let's see. It's not too clear, huh? Let's see. Is there a way to make the lines thinner? I think there was a way to make the lines thinner. Or I could just go back and make the velocity a little bit less. Let's make it 23,000. So it won't come on itself again and again. You know what? I think my original one was better. I'm gonna go X, don't save. I had a better looking line before. Back to that. Yeah, I see. I don't know how I had done it, but see, the lines are a little bit thinner here. So let's go to the original. So let's say 23,000. So what is happening? Actually, it's starting at it's starting at 1 AU. So this is the start. It's actually not as simple to guess what's going to happen. Notice we guessed that it's going to spiral into the sun. That's actually not what's happening. Starting at 1.5 AU, goes here, and this is this is less than 1.5. Remember, 1.5 times 10 to the 11th is 1 AU. It's the distance of the Earth from the sun. So it starts here at 1 AU, goes here, and reaches the maximum position here, but that's not even 1 AU, it's less than 1 AU, right? Then it comes, and then the closest approach to the sun is negative 0.5 is this one, negative 5 times 10 to the 11th. So it's somewhere between 5 times 10 to the 11th to 1 times 10 to the 11th, right? This is 0.5 times 10 to the 11th. And then so 1 AU would be here, essentially. Okay? So how would you characterize this shape? An ellipse, kind of, right? It starts at 1 AU, goes to a little over a third of an AU, comes, but then each time it's coming, it's getting further away from the sun. Isn't that weird? So it's going like that, comes, then goes further away from the sun. This part of it stays kind of the same, this distance. But that part goes further and further away. So what's happening, it's getting a slingshot effect. It's coming, the sun's gravity is slinging it further away. Isn't that interesting? So this way, we could use this way if we wanted to go, let's say you keep doing this for years and years and years, the satellite will keep going further away and you can get to Mars that way. You know, or some other planet further away from the sun. So this is called the slingshot effect, and it's used by NASA when they send satellites. Okay, you could go, let's say, slower even. Oh, it's so much fun. You can just put any initial condition that you want. Let's say 20,000. Ooh. And what? Let's make it so that this is, the scale is, I want to make it so that the scale is what it truly is, right? So if this is 1, and this is 2 times 10 to the 11th, that's 1 times 10 to the 11th, right? So if we want to see the way that it's truly going to look, we need to scale this thing so that this is twice the length as that. You see? That, then you can actually see it for truly what it is. So, something like that. Is that true? Yeah, so then this, from the length from here to here, should be the same as the length from here to here. So it's looking more like an ellipse now, right? Now the gravitational slingshot effect is even more, slinging it further and further away. So if I do even slower, let's say 15,000. Okay. Oh, so cool. So not only can this be a way to see what would happen to the Earth if it had that velocity, but this could be a way of saying what happens to a satellite when it's launched from the Earth. You see? So it doesn't have to apply to the Earth. You could say, what if I launch a satellite from the Earth going this way, and then what would happen to it? And there you have it. Simple Excel is doing a complex operation like this, right? You say, oh, okay, in 3 years, the satellite ends up here. You see? Now, if there was another planet there, let's say Mars can do its own slinging, and then it can sling the satellite to Jupiter. You see? So you can plan it so that this goes like this. Then you say, oh, now come around Mars, sling, and go to Jupiter. Now that would be a good program maybe you can write. You say, oh, okay, there's another planet here. Now how about its effect on that satellite? And then write that program. And say, whoa, where does it end up 2 years after that? All right? Just by doing another equation for that. Because by the time it gets here, if there's a planet like right there, its gravity is going to dominate over the sun's gravity on that satellite. Right? So you don't even have to worry about the sun's gravity anymore. Then that guy is going to sling this guy. So it's really cool. If I go even slower, let's see what happens, 10,000. Oh, the shape completely changes, right? Go like that. The sun slings it all the way out to, this is almost 5 AUs. So that's where Jupiter is actually. So in less than a year, you're already you're already where Jupiter is, and then you come around and you go out to the further solar system. Okay? Of course, though, if Jupiter's like right there, Jupiter might capture it, and then it might be a satellite of Jupiter. So we haven't taken into account the gravity of Jupiter. So, but you can kind of see how things get really interesting here. You can put whatever you want. And you could even change anything else that you want. You can say, what if this is a satellite that's not only going in the Y direction, but is going in the X direction? Let's say X is negative 10,000. So what did I do? Now, the satellite is going up at 10,000, and then this way at 10,000. So it's going at a 45-degree angle. Now what is its path going to look like? You see? So it doesn't necessarily have to go this way. You see it's going 45 degrees? It goes, comes around the sun, and if I want to know where it is further more years later, all I do is just go back to that page, copy, paste down more. As many rows as I want. So all I do is just go back here and then just drag it down further. Okay? Or I could even do some situation like this. What if X initial is this and Y initial is and then I'm going to copy, paste it here. Then I go over here, I say 0. So what did I do now? What situation did I create? There is a comet coming in whose location is 1 AU away and 1 AU away up this way. So now you're completely a different scenario you're analyzing, right? So you're analyzing what's going to happen if this is the sun, 1 AU, 1 AU, then if there's a comet coming in this way, whose velocity is 10,000 meters per second. And the Y component of velocity is 0, so it's coming straight. It's probably going to do something like this, right? Right? So let's see. Yeah, so ended up doing this. Goes like that, curves. Right? Powerful program, right? Just simple. I'm surprised. When I first did this, I was like, I wasn't sure if Excel would be able to do this. And then I go, wow, it actually works. Very accurate. You can do any condition, initial condition, then it gives you the path of that. Let's say negative 20,000. It's interesting. If I make it faster, then it comes and the sun cannot fling it away as quickly. It comes and it makes several times around. You see? Whereas when I made it too slow, it comes and then just shoots out. So it's kind of surprising. Comes, goes around, comes, goes around, comes, goes around. Wow. So you can do anything that you want. Cool. So now you know how this works. See if you can reprogram that, make it whatever you want, your own. Use it to predict what's going to happen in a certain scenario. That'll be a good extra credit here. Okay, so now we've done the problem where we had 2 stars and we found out the gravity on a 3rd star. We asked questions such as where is the force 0, where is the gravity some number. Now let's do cases where I want to find the gravity of a ring planet and the gravity inside of a spherical planet. So some integration problems. So we haven't done any integration yet. So if this was electricity and magnetism, physics 3, I would have covered how to do the electrical field of a rod, semicircular rod, electrical field of a cylinder, plate, ring, spheres. So we do a little bit more different kinds of shapes in physics 3. But in physics 2, I'm going to focus on things that are more realistic when it comes to planets and stars. So a spherical shape, maybe a ring shape, maybe a plate. Those are more realistic. So gravity of a spherical plate and ring shapes. So let's say you have a ring. And you say, when would that happen? A ring? Well, it would be such as the rings of Saturn, right? The rings of Saturn have some mass and have certain radius, right? They would create a gravitational field at any location in space. They would attract you just like Saturn would attract you, right? So imagine that this ring has a certain mass and a certain radius. What is the gravity that it causes any distance, any x distance away from the ring? We can say, what is the gravitational field of that as a function of x? Once you find the gravitational field that the ring creates, you can find what someone would weigh over there, right? So we can say, what is the general equation for g of x, and then b, apply this to the rings of Saturn to find out how much a person would weigh So apply this to the rings of Saturn to find out how much a person would weigh, distance of 1 AU from the rings. And let's say it's a 200-pound person. Okay? So then how would we find out the general gravitational field? You take a piece from here, you use some symmetry. You say that piece creates a gravitational field there towards it, right? Then this piece over here creates a gravitational field towards it, dg, right? So if you take a ring like this, one piece from here, one piece from here, they create a field this way, create a field this way, and then since it's symmetric, their y components cancel and their x components double, right? So dg total is equal to 2 dg x. In other words, their x component. This is a dgx right here. And then they double the x component doubles. And then so dgx is going to be dg cosine of this angle, right? Theta. 2 dg cosine theta. So then if this triangle is x right here, this is r, right? And then this is square root of r squared plus x squared. Right? So what's going to be? 2 dg is going to be what? It's the gravitational field created by one of those pieces. Well, one of those pieces has a mass dm, right? So the gravitational field created by that is going to be g dm over r squared. Remember, the gravitational field created by a point mass is the gravitational constant g times the mass of that mass divided by the distance between this and this square, right? So then you're going to have here 2g dm, and then r squared is going to be, this is r, right? So r squared is just going to be r squared plus x squared. R squared plus x squared. Then cosine theta is going to be what? Cosine theta is going to be x over square root of that. So x over square root of r squared plus x squared. So then it's going to be 2gx over r squared plus x squared to the 3/2 power dm.